Okay, greetings. Welcome back. Today is really the last sort of mathematically intense um, lecture of the course. We've been talking about how sound is the composition of a whole bunch of sinusoids added together, sine waves and cosines, and you can find those sines and cosines by using the Fourier transform to taking advantage of orthogonality. Basically, when you multiply any signal by a cosine, you get only the amplitude and the phase of that particular cosine in the average of the result. And so what I want to talk about today really is how to use that in order to analyze natural speech. And there's some things in here that only work on some computers. So in particular, this first section, I want to try to use IPyWebRTC to record speech. I think that actually still works on Windows, but no longer works on Mac. So here's information about IPyWebRTC. There's the GitHub repo, and the general idea is you can use this to record a movie on your in Python. The idea is that you create a video recorder object and you assign that to some name recorder, and then you create the file name into which you'll save the result, and the format, which might be MP4. We're going to only record audio, but Apple Macintosh by default now has for about a year has disabled recording directly into the notebook. So we're going to have to try to use a different method. Let me go through and show you the code, how this is supposed to work. So if we wanted to record IPyWebRTC, the first thing you would want to do is to install it. And you can do that using pip install, the same way that you would install anything else. The exclamation point here means that it should run a shell command, runs an operating system level command, such as pip. And you can see that the result I get is requirement already satisfied. And that's because I've already installed IPyWebRTC, so I already have it available. Now we can import it and create a camera stream object. We're only going to record audio. So I'm going to create an audio recorder um, reading from this stream. So this means that I'm taking an input from the audiovisual devices on my computer, but I'm only going to record audio. So I'm going to constrain it to be audio is true, video is false. Right, so it creates a stream from all of the devices on my computer, and then records audio into the output. And if I try to run this, it says that there's an error displaying the widget. And that's just because Apple has disabled this functionality on Jupyter notebooks in Apple computers. And so instead, what I'm going to have to do is show you a different way that you can record. So here I can print the recorder, and it shows that this is a recorder, but the content of the recording is null. You can see that the value is B means binary, but it's binary with 0 consecutive characters. So this 2 quotes in a row means that the value is a binary string with a length of 0. And you can see that it has the constraints I gave it. It has audio is true and video is false. But because Apple doesn't permit this to be used, it stopped. I forgot to start transcription. So let me go ahead and start the transcription in English. And that will mean that when it shows up on YouTube, that you'll be able to see the text of everything that I say from here on out. All right, so since Apple has disabled recording of audio directly into a Jupyter notebook, I'm going to use a completely different method. I'm going to use you can use many different kinds of recording software. I'm going to use one called Prot, which is distributed by the University of Amsterdam. So actually, this is not. I don't think it's not. The default is not University of Amsterdam. There's so many different tutorials for Prot. Um, hmm. Oh, here we go. Let's go to the Wikipedia page for it. Prod is a free open source computer software package for speech analysis and synthesis. And it's normally, it's now distributed from GitHub. We can, let's see. I installed this a long time ago, so I'm not sure what the best way to install it is now. So here's its GitHub. Here we go, official website. That looks like the right place to go. Let's go to the official Prot website. And then if you want, you can download Prot from this website for either Mac or Windows or Linux or Raspberry Pi or Chromebook or any other operating system that you like. In my case, I already have it installed, so I'll just open it. And what I want to do is I want to create a new audio file. So I'm going to create a new record mono sound and let me record. I want to record a mono sound from the input, which is my AirPods, and I will just hit record. Invalid sampling rate. Oh, interesting. That hasn't happened to me before. Let's see if I can record at 8,000 hertz. No. Well, this hasn't happened before. We might have to go with some other method to get audio. Oh my goodness, I can't, it seems that the Apple has locked up recording, so I'm not able to record in any way, shape, or form audio onto this computer. Let me try, let's try, well, there's a lot of built-in tools on Apple. Let me just go to the web and get something from the web. So let's look up timid examples. So just get any natural audio. In this case, I'm going to go ahead and download an audio sample from Timid. And let me go to my downloads folder here. And I think this will actually not be in, let's see if we can play this directly or if we have to change the format, because the original Timid format was not the normal WAV format. Oh, well, here's an interesting one. Let's open this waveform. That looks fun. Fast speech number 1. And let me edit it in Prot, view and edit. And let's hear what it sounds like. I'm not hearing it at all. Are you hearing it on your end? It seems that audio playback has been disabled on my computer. Maybe that's the problem. I see. Mr. Hossein, you said that I forgot to upload lecture 9 video on YouTube. Yes, I'll check that. None of you are hearing these audios either.
The way that the heat built into the surface, you know.
Oh, okay. Now that it's playing, it's just playing very strangely. All right, I'm going to assume that that's there, and I'll go ahead and load it into the Jupyter notebook. Let's let me open it again, and then that was fast speech 1. Let's open that, and then let's save it as something else. Let's save it as a WAV file, and let me save it into the directory where we just were. That'll be documents, GitHub. Intro Speech Understanding, 2025 Spring, Lecture 10. And then let me record this as, let's call it speech.wave. All right, so download some kind of audio file that you can work with. And then let's go back to the Jupyter Notebook and try to read it in. Now that we've downloaded that audio file, we can read it in using Librosa. There's a number of packages we can use to read and write audio file, but Librosa is a particularly useful one. If you look up Librosa online, you can see that it has quite a lot of functionality. It has core I/O and digital signal processing. It can calculate spectral representations like the short time Fourier transform. It can also just do a number of different kinds of display. Let's see, do we have, here we go, display. So it can display spectrograms and individual spectra. So let's make sure that we have it installed. We'll do pip install Librosa. And it says that it gave me no response, so I'll assume that it's working. Oh, it gave me no response because I put the -q option to avoid having a response. And now I'm going to read in speech.wave file that I just stored. So I will use Librosa to read it in, and I'll set the sampling rate to 16,000 samples per second because the default sampling rate was much larger. So Librosa load will automatically rescale the sampling rate to whatever I specify here, 16,000 samples per second. And then I'll create a speech time axis, which is as long as the speech file, but divided by fs, so that it gives me the time in seconds. And then in the subplot, I'll show the speech time axis on the x-axis and the speech waveform on the y-axis. Let me go ahead and use Librosa then to read in that audio file and to show the resulting audio file on the y-axis and the time on the x-axis. It seems that it takes a long time to load. There we go. Now we've loaded the entire audio file. You can see that actually all of the reason it took a long time to load is because it's 18 seconds long, but most of it is silence. All of the actual speech signal is between about 1.5 seconds and about 4 seconds. So we could actually just chop it up. Let me go ahead and create a new window here. And let's just take the part of the speech signal, which is between 1.5 and 4 seconds. Let's say speech short is equal to speech from 1.5 times fs up to 4 times fs. And then let's go ahead and plot that. Let me create a new speech time axis, which is the same length as SP short. The slices need to be integers, so let me just wrap those in the integer mark there in order to convert them to integers. There we go. Now we have something which is mostly speech. Oh, it looks like I started it just a little bit too late. It looks like it should be earlier than 1.5 seconds. So let me make it 1 second. Let's see if that works. There we go. There's the entire speech content. Let me actually call that speech. So I will take the original speech array and replace it with this new array, which is much shorter, only about 3 seconds long. That'll be a little bit easier to work with. All right, so now we have a natural speech signal. Let me see if I can play this speech signal or if my Mac is actually really causing a oh, import IPython, I guess.
The way that they keep elephants in the circus, you know.
Okay, there we go. That's a speech signal. A little unclear, but it's a little unclear apparently because the original speaker was talking very fast. This is a speaker saying that's the way that they keep elephants in the circus, you know. And this speaker is very fast. They said that that complete sentence in about 2.5 seconds. That is the way that they keep elephants in the circus, you know.
The way that they keep elephants in the circus, you know.
All right, a very fast utterance. All right, now that we've got that audio, now we know that that audio is created by the vocal folds are closing once every, about 100 times a second or maybe 200 times a second. Those vocal folds closing 200 times per second are exciting the formant frequencies of the vocal tract. We could analyze that by multiplying that audio with individual sine waves, and then we could see the content. In fact, let me zoom in and show the details maybe here at around 700 milliseconds. Let's zoom in and show a plot of the zoomed in part. So let me just copy this part and create a new figure. And let's just zoom in a little bit and show, hopefully we can see the individual vocal fold closures and the resonances afterward. If we zoom in close enough, let's say we'll zoom in from 0.7 times FS to say 0.8 times FS. We'll just show 100 milliseconds. And we'll wrap those in int so that they can be used as slices. And the speech will, so that's the time axis, and let's also do the speech from 0.7 times FS up to 0.8 times FS. There we go. Let's see if that gives me a plot of those 100 milliseconds. There we go. There's those 100 milliseconds. So that is the way. So this is, I think, the vowel A, and that is the way. That's the way they keep elephants at the circus, you know. This is maybe the A in way. And you can see that it looks like maybe here and here are the glottal closures, right? The glottis is closing maybe 200 times per second. So here we have 0.02 seconds. And in that 0.02 seconds, the glottis closes 1, 2, 3, 4 times. So 0.005 seconds per pitch period. So a pitch of about 250 hertz, right? 4 times in 0.02 seconds means about 250 times per second. And that those glottal closures are exciting this first formant resonance. You see the ringing of that large sine wave. So if we multiplied this by a cosine at exactly this frequency, we should get a very large amplitude at exactly this frequency. But you can see there's a lot of information here at other frequencies as well. There are these small little glitches, and those are probably at around the second and third formant frequencies of the vocal tract. And so what we really want to do is to find out what are all of the different cosines and all of the different sine waves that are making up this signal. The other thing you can see is that they change. Here we have one set of cosines. Here we have a completely different set with completely different amplitudes. And so over time, the difference between real speech and synthetic speech is that in real speech, those amplitudes and phases of all of those cosines change over time. This first formant resonance becomes slower, actually. Its amplitude becomes smaller, and the phase becomes a little bit different as well. And so we can't do this thing of just multiplying by a single Fourier transform over the entire audio. We have to take the audio a little bit at a time. And so that's what I've described here. A Fourier transform finds out which tones are present in the sound, but natural speech changes over time. And especially if you have somebody who is speaking as quickly as this talker, right?
The way that they keep elephants to the surface,
This talker is speaking so fast, her speech is changing very quickly over time. And so in order to solve this problem, we use something called the short time Fourier transform. And what that is we just divide the speech into overlapping frames, right? We chop it up. We'd say, okay, let's just analyze this part, and then we'll just analyze this part, and then we'll just analyze this part. We divide it up into short windows and take the Fourier transform of each of those short windows in order to find out what are the amplitudes and the phases of all of the cosines that make up the speech within each window separately, because each window will be different. The spectrogram is defined to be the log magnitude of the short time Fourier transform. So the STFT is the Fourier transform of each of those windows, all stacked up into a matrix. That's a complex valued matrix. It has imaginary part and real part. And so we use the magnitude, the absolute value, in order to get rid of the phase and keep only the amplitude. And then we use the logarithm because some of those cosines will be much, much louder, much, much higher energy than others. So let's go through that in three parts. First of all, we'll divide the speech into overlapping frames. Second, we'll take the Fourier transform of each of those frames. And third, then we'll take the log of the magnitude. So first of all, we'll divide the speech into overlapping frames. Let's say that each frame is going to be 25 milliseconds long. So we'll say that the frame length is 0.025 times the number of samples per second. And we'll make them overlap. They will overlap by 15 milliseconds. And so the step, each frame will start 10 milliseconds later than the one before it. So the frame skip, or the step size, the time from the beginning of one frame to the beginning of the next here, we're going to make that be just 0.01 seconds. And then the total number of frames we need is the length of the speech minus the frame length divided by the step. So the first frame takes one frame length worth of samples. And then after that, every step worth of samples, we have one more frame. So when we subtract the length of the speech minus the frame rate, minus the frame length, that gives us how many steps we can take. And then we divide that by the length of the step. And that'll give us the frame length and the step. And in this case, we're going to find that the frame length is 400, the step size is 160, and the number of frames is 297. So I'm going to have, the sampling rate is 16,000 samples per second. 16,000 times 0.025 is 400. I have 400 samples in each frame. 16,000 samples per second times 0.01 is 160. So each frame starts 160 samples later than the frame before it. And then the number of frames will be 297. And so what I'm going to do is what I've already done here actually is I created a matrix called speech frames, which is a matrix that has the number of rows is equal to the length of one frame, and the number of columns is equal to the number of frames, right? And each frame, so the frame number here, the frame number goes from 0, 1, 2, all the way up to the number of frames. Each frame is equal to the speech signal from that frame index times the step size up to that frame index times the step size plus the frame length. So by doing that, then I can plot that as an image. So I'm going to show an image, which is just those speech frames. And I'm going to make the origin be in the lower left corner. That's what this origin lower means. So here's the origin in the lower left corner. And you can see what you're seeing here is kind of the overlap between frames, right? You can see basically the pitch pulses where it goes down and then up for the pitch, and then down and then up, and then down and then up again. And from one frame to the next, those pitch pulses shift over by 160 samples. And so that shifting of the pitch pulses gives us this sort of striping look where each frame is, let me plot just one frame so you can see what just one of those frames looks like. Let me plot frame number 50. Then we plot speech frames number 50. And then we'll say that the title will be subplot set title will be frame number 50 plotted as a waveform. Plotted versus sample index. And what we see is, so this is the column number 50 from this image. And you can see that in that column, we've got this first peak of the waveform, and then it goes down, and then it goes up, and it goes down. And you can see that right here. First the peak must be this darkness. Oh no, maybe we're right here. So the peak is this bright spot. And then it kind of goes down, and then there's this big negative, which is that dark spot, and then immediately afterwards there's a bright spot, which is the next peak. And then here's another downward pulse, and then an upward pulse. Over here, there's another downward pulse, and then an upward pulse. And all of those are showing up here as this bright, and then dark, and then bright, and then dark, and then bright, and then dark. Let's see if we can count those. Here we have 1, 2, 3, 4, 5, 6 of those, or maybe only 5. So we have 1, 2, 3, 4, 5. It looks like maybe these 5 are the 5 that are showing up as bright spots in this 50th frame in this speech image, right? So that's kind of cool. It's showing us the pitch period, but it's not really showing us anything else except the pitch period. And we can see how the pitch period changes. It's the pitch period is longer in this part, and then it becomes shorter over in this part, and then it becomes much longer over in this period, over in this part. We can see how the pitch period is changing over time, but we can't really see, for example, what vowel it is. You know, she says, that is the way that they keep elephants in the circus, you know. You can't tell the difference between the word elephants, which must be in here somewhere, and you know, which is over here. You can't tell the difference between those vowels. Those don't show up. In order to know the difference between the A and the O, we need to be able to see the format. Right? You remember from last time and a couple of times ago that A has a high frequency F2, O has a low frequency F2. And so in order to be able to see the difference between elephant and zoo, we need to be able to see not just the pitch, we need to also see the formant. And so for that, we need to take the FFT. And that's simple, actually. We can just take numpy.fft.ft and specify along which axis do we want to take the Fourier transform. We're going to take the axis number 0. So this is axis 0, axis 1. The column, the row index is axis 0, the column index is axis 1. If we take the FFT along axis 0, then it will take each of these frames and compute its Fourier transform. And then we can show the result. I'm going to show just the absolute value of the result. Now I'm going to show just the part up and through half the frame length. And what I get then is I get the FFT. You can see here's the speech. There's the way they keep elephants at the circus, you know. You can see the syllables in it, but they're only, all of the energy is down here at the very low frequencies. Let's actually create a frequency axis. The number of frequency bins, because we're taking an FFT, the number of frequency bins will be exactly equal to 400. And that corresponds to 8,000 hertz. So let me create a frequency axis, which will go from, which will be have frame length samples in length, but the upper limit should be the sampling rate, fs, and it should be divided by frame length. So by the time it gets to sample number frame length, I want the frequency to say fs. And then let me try plotting in the image. Can I specify axes in ImShow? Actually, I'm not sure. Let's look it up. At Plotlib ImShow, X, can I specify the frequency axis and it doesn't look like I can specify the x-axis and the y-axis. Let's search for help online. How do I specify x-axis and y-axis in NumPy ImShow? X-axis and y-axis labels. How to add axis labels. Well, this is not helpful. All right, there's probably a way to do it, but it looks like it's not obvious. And so instead, we're just getting the integer. Here's the frame index, and here's the frequency bin. The highest frequency bin here is the Nyquist rate, which is the sampling rate. If the sampling rate is 16,000, this highest frequency is 8,000. And you can see that of those 8,000 hertz, only the lowest frequencies have energy that's high enough to be visible in this image, right? The real problem with this short time Fourier transform is that almost all of the energy is in these first 2 or 3 harmonics of the pitch, right? And you can kind of see that in the waveform. But if we go back to the waveform that we plotted, you can see that the pitch is maybe 250 hertz, and maybe the second harmonic at 500 hertz has a lot of energy, and none of the others have any energy. All of the others have much, much smaller energy. There's certainly information at very high frequencies, but that very high frequency information has a very low amplitude. And so that's what we see here. We see lots of energy at these very low frequencies and no energy that we can visualize at the high frequency. The way that we solve that problem is by taking the logarithm. Rather than simply plotting the absolute value, I want to plot the logarithm of the absolute value. That will compress the high amplitudes, right? Logarithm is a compressive nonlinearity. Let's look it up just in case you haven't seen this recently. Let's look for Wikipedia logarithm. All right, so here's plots of the logarithm. Normally we use the log base e of x. So if this is x on the x-axis, the logarithm is on the y-axis. And you can see that the main point of the logarithm is that very large values are not very different. When you take the logarithm of e and the logarithm of 10, the logarithm of e is 1, the logarithm of 10 is just about 2. And so the larger it gets, the output also gets larger, but much more slowly. Whereas very small inputs cause very big differences in the logarithm. And so that will help us here because it will mean that these very large amplitudes get compressed, and it will sort of emphasize these smaller amplitudes that we're not seeing. So what kind of logarithm should we take? The standard is something called the decibel. And this was standardized by the Bell Telephone Company in 1910. This was originally designed based on the rate at which power decays in telephone lines. Power decays in telephone lines at about 1/10 every 10 miles. And so they said, let's just take the logarithm of the absolute value and multiply that by 20 in order to specify how many miles we've traveled along the telephone line. So we can use NumPy log 10 to take the logarithm of the absolute value, And then we can multiply it by 20 to go to this standard. And let me show you the standard. The standard is called the decibel. And this is a standard unit of measurement named after Alexander Graham Bell. It's a it's a standard accepted unit and has been in use since about 1910. All right. And so we'll simply take that speech short time Fourier transform. We'll take its absolute value. Then there's this one more thing we're going to do. We're going to divide it by its own maximum. We'll calculate the maximum absolute value and divide the magnitude short time Fourier transform divided by its own maximum. That means that the maximum is now 1, right? I've taken whatever was the maximum value before and I've divided everything by that maximum. All right, the logarithm of 1 is 0. And so now when I take the logarithm of this MSTFT over max MSTFT, that logarithm will all be negative numbers. Everything will be 0 or less. And I don't want to pay attention to very, very small values. And so what I'll do is I'll take the maximum of 0.001 or this absolute value. Right? This is a value that's always 1 or less. And this means that it's always going to be greater than 0.001. So when I take the log base 10, it'll always be a number between the log base 10 of this number, which is -3, and the log base 10 of this number, which has a maximum value of 0. So this logarithm will all be values that are, this logarithm will all be values that are between -3 and 0. They'll all be between -3 and 0. So then if I take 20 times those values, I'll have a range of decibels that are between -60 and 0. And that's usually the range over which you have useful information in speech. The threshold of hearing is 0 decibels SPL. The normal conversational speech is about 60 decibels SPL. And a very loud rock concert might be 100 or 120 decibels. So usually the whole range that you want to see is only about 60 decibels. At the very most, it might be 100 decibels. And so you can see that by compressing, basically by keeping everything between -60 dB and 0 dB, what I've done is now we can see all of the syllables. That is the way they keep elephants at this. Oh, here's the S in circus. Circus, you can see the circus. At the circus, you know. And then this last part is the you and then no. And you can almost see like all of the syllables in that speech that she's saying. That's the way, I guess. As the way that this F2 glide here is definitely way. As the way they keep. I think this must be the K. They keep elephants. I think this might be the L. Elephants. Oh, this is the S in elephants. That's the way they keep elephants. Here's the S in elephants. At the this little bit here must be at the. You can see that there's no. She speaks so fast that there's no stop between the at and the. So it's at the circus, you know. And suddenly, we've got all of that information. You can see, for example, that that's the way they keep elephants. Here's the S, and you can see the very high F2, elephant. Well, I mentioned way. You can see the upward gliding F2 in way. You can see the first formant is low for way. The second formant is high for way. For that, the first formant is a bit higher. It's about the same actually. But the second formant is much lower, and then it goes up for way. That's the way they keep elephants. Elephants, I think. Maybe this is the with a very high F2. La, this is the in elephants with a very low F2. And then funt with a very low F2 at the circus. And then the I in circus is a little bit higher, but not as high as the E in elephants. So you can see suddenly all of that, all of that information that was kind of invisible here has suddenly become visible in this thing that we call a spectrogram. with practice, you can learn to actually read these off. You could learn to like go through and figure out, okay, this F2 is at these particular frequencies, and you could read off exactly what vowel it is and exactly what fricative it is. I was mentioning that these things are obviously S's. You can see, circus, because it has this high frequency energy, and so it's possible to learn to recognize the speech from this representation. And that's essentially what an automatic speech recognizer does. We train a neural net to be able to understand what each of these spectra is and to piece them together to form a word. I want you to know all of these steps. I want you to know about chopping the waveform into frames. I want you to know about taking the Fourier transform of each frame. And then I want you to know about taking the decibels by taking the logarithm of the magnitude of those frames. But all of those things can be done for you using Librosa. This one, Librosa.stft, will actually do the first two steps for you. It will chop the signal into frames and find the STFT. So here we take the input, which is Y, the input waveform, the length of the FFT, the hop length, which is the step size between the beginnings of the windows, the window length, which can be none, or it can be a specified window, a window length, the type of window, what shape is the window that you're using, and so on. And so here's the parameters. Y is the input signal, and FFT is the length of the window, is the length of the FFT, hop length, window length. And then the return is just D, which has a shape of the number of FFT samples times the number of frames. Right, the number of rows is equal to the half of the number of FFT samples. The number of columns is equal to the number of frames. So this is just exactly those first two steps. This calculates the STFT. So we'll take a Librosa STFT, which is Librosa.stft of the speech, with a hop length equal to the step size, and with the window length equal to the frame length. And then only one more step, and that is to convert it to decibels. And that can be done using Librosa amplitude to dB, which takes an input, which is a real valued input. And so we have to take the absolute value first. So we'll take NumPy absolute value of the short time Fourier transform, and then we'll convert it to dB. And Librosa amplitude to dB actually uses a minimum value, which I think is a default of 10 to the minus 5 instead of 10 to the minus 3. So by default, Librosa has a total range of 100 dB, and it scales the top to be at 80 decibels. So it has a range of 80 to 100 decibels instead of just 60. All right, so we'll convert it to decibels, and then we'll use Librosa display. Also does something nice. Let's look up Librosa display. Librosa display spec shows the data. It's a matrix, for example, a spectrogram. It has a sampling rate and a hop length and a number of FFT. Librosa display will do this wonderful thing. It will plot the frequency axis in whatever frequency range you want. You can specify a log frequency range, or a MEL frequency range, or a EQT scale, whatever that is. You can also plot the what are these categorical types? You can plot the time in hours, minutes, seconds, or samples. So we can specify, what have I specified here? Sampling rate is FS. The hop length is the step size. The x-axis, I want the x-axis to be in seconds. And the y-axis, I want it to be in hertz. And so this is a huge improvement over NumPy MShow. What this does is it allows us to plot the y-axis in hertz rather than in FFT bins, and the x-axis in seconds rather than just in frame numbers. And so when I plot it, I can get, this is the way they keep elephants in the circus. You can see that this is the same spectrogram as this one. What if I can stretch it out a little bit? Let's see, can I specify a figure for this? Axis equals none. Does axis allow me to specify the Matplotlib axis? Yeah, axis is a matplotlib axis. So let me actually create a figure of the same length as this. And so I can spread that out a little bit. All right, and then let's see, I'll say axis equals subplot. Let's see if that works. Nope. Oh, not for STFT. I want that for the spec show. Right? Hmm. Let's see. Oh, ax, not axis, ax. Let me try ax and see if that works. Oh, there we go. Now I got a long window so we can compare these two. We can see that it's basically the same information. That's the way they keep elephants in the circus, you know. That's the way they keep elephants in the circus, you know. The scaling is a little bit different. When I scaled mine, I made it only from -60 to 0. Here it's being scaled from -100 to 0. So you can see that some of the very low frequency, some of the very soft sounds here have been made a little bit brighter here. You can also see it's used a different color scheme rather than this green-blue color scheme that was the default for NumPy, the Matplotlib. This one is using a blue-orange color scheme, which is a little bit more visible. But otherwise, essentially what Labrosa has done here is to plot exactly the same spectrogram that we calculated on our own, but it's given us this one extra piece of information. It's given us the time axis in seconds and the frequency axis in hertz, so that we can see exactly where the different sine waves are. You can see that here's the pitch frequency and the second and third harmonic, fourth, fifth, sixth, seventh harmonic. This dark band here is the first formant. This dark band here is the second, and so on. This is how speech recognition works. This is the basic idea of automatic speech recognition. Next week, we will use a predefined automatic speech recognizer. We'll use the Google Speech Recognizer to actually recognize arbitrary sounds, arbitrary speech. But basically, what I wanted to show you this week is how the Google Speech Recognizer is working behind the scenes. What it's doing is it's calculating a spectrogram like this, and then it's recognizing these patterns. It's saying, oh, this is the vowel A, this is an S, this is an S, this is the vowel E, this is the vowel, this is an L, this is an F, right? So it's finding this. That's the way they keep elephants at the circus, and it's recognizing each of those sounds by recognizing the pattern in the spectrogram like that. The homework for this week is to reproduce those three parts of the spectrogram: converting the waveform to frames, and then converting the frames to the short time Fourier transform, and then converting the short time Fourier transform to the spectrogram. So let's look at those help files. First of all, the docstring says waveform to frames. We want to chop a waveform into overlapping frames. We're given the frame length, which is an integer, the length of the frame in samples. We're given the step size, which is the length of the frame which is the step size between the beginning of adjacent frames and samples. And we're given the waveform, which is a NumPy ND array of length capital N. And we want to return a matrix which has frame length number of rows and num frames number of columns, which is that waveform chopped into frames. So let's open that up and see how that should be done. Let's see, so we want to get rid of this runtime error. And instead, what we want to do is we want to first calculate the number of frames. All right, so let's see, number of frames should be the length of the waveform minus the frame length divided by the step size, right? So the length of the waveform minus the frame length is how many samples need to be covered by stepping from one frame to the next. And then the step size tells us how many samples are skipped between consecutive frames. I want to convert all of that to an integer. So I'll wrap that with integer. Now I want to create my output. My output should be a matrix called frames, which should be, let me initialize it with zeros of size frame length by number of frames. And then I just want to fill each and every frame, or frame in range of number of frames. I want to take the frames matrix in that particular column. And that particular column should consist of the waveform from step times the frame index up through step times the frame index plus the frame length. And then I want to return the matrix of frames. Let me see if that gives me a nice picture. If I've done that correctly, then I should be able to load homework 10, and then I should be able to plot frames, which should look exactly the same as the frames that I calculated before. There they are. There's all of the different pitch periods. And so, yeah, that looks like that's roughly the right sort of image. Now let's look at how do we convert it to a short time Fourier transform. Now we have the matrix of frames, one frame of samples for every step size. And we want to convert it to a short time Fourier transform, which is just the complex valued Fourier transform of every single frame. So I think I can do that just using np.fft.fft. The STFT should be np.fft.fft of the frames along axis 0, that is along the column axis. And oh, I'd better return that. So let me return the STFT. Let's go back and take a look and see if that worked. Yeah, that looks like the STFT. There you can see the syllables are showing with strong energy at the bottom and with not much energy up above. And then finally, I want to convert that to a spectrogram. So I want to calculate the level in decibels of each complex valued sample of the STFT, normalized so that the highest value is 0, and clipped so that the lowest value is minus 60 in decibels. All right. So that means, first of all, I want to convert it to magnitude. Let me calculate the magnitude short time Fourier transform. MSTFT is just the absolute value of the STFT. And then the max of the MSTFT is just numpy A max of the MSTFT. And then I want the normalized MSTFT will be the MSTFT divided by its maximum. And I want to take the maximum of that number, or 0.001. Right, that allows me to calculate something between 0.001 and 1. And now I want to return 20 times the log base 10 of that normalized MSTFT. And that should give me, normalized MSTFT is between 0.001 and 1. And so this should give me something that's between minus 60 and 0. Let's see if that gave me the right values. And there we have the spectrogram. Let's check and make sure that that matches with the grading rubric. And that looks like that matches with the grading rubric. So we should be able to check it in. Let me go to GitHub Desktop. And let's say homework 10 is done. And commit that. And then push it to the origin. Now, if I go to my own GitHub account, let's see, I think I'm logged in as a student here. Let's find out. Yep, that looks right. So we'll go to the intro speech understanding. Let's go to homework 10, make sure that it's there. All right, looks like it's all there. So let me copy this URL and go to the homework 10. It says hidden from students. Let me see, can I change that here? Let me make that visible to students. Now, if you go to homework 10, you should be able to copy in, enter the URL of your copy. You should be able to copy in your copy of the URL. All right. I guess that lecture 9 has not yet been uploaded to YouTube, so I will first upload lecture 9 and then lecture 10. Hopefully I still have a recording of lecture 9. I'll have to go back and check. I'll upload both of those lectures, and then you can follow those in order to make sure that you get the homework so that you can have your homework graded and everything. Meanwhile, let's go back and take attendance. Okay, please go ahead and register your attendance using this code. I think there are 11 of you here, right? 3 people so far. Thank you. 6 people so far. Are there another 5 people? Please go ahead and use this code to register your attendance. Up to 8 people. We have another 3, up to 10 people. Is there another 1 person logged in, or is somebody logged in twice? Looks like everybody is logged in separately as far as I can tell, so there should be 1 more person. Does anybody else want to register attendance before we all log off? Last chance to register attendance if you haven't yet. Going once, going twice, 3 times and sold. All right. Oh, good. Thanks, everyone, and I'll talk to you next week. Thanks. Have a good week.
Thank you,
Bye-bye.
Sensei.
Thank you.